Okay.
Welcome back, everybody. Start of our next session, Sam Hopkins will talk about the nearly tight sum of squares lower bound for the planted clique.
Okay, thank you all for coming. This is a paper by Boaz Barak, me, John Kellner, Pravesh Kothari, Ankur Moitra, and Aaron Patechin, the last of whom is on the market this year. So, the planted clique problem. You receive as input an n-node graph and the promise that it was generated according to one of the following two distributions. One is gn half, the Erdős-Rényi graph with parameter half, illustrated on the left, where every edge is present with probability half independently. And the second, which we'll call the planted distribution, you first sample a copy of gn half and then add to it a random k clique. So sample k edges uniformly at random, or k nodes rather, illustrated in pink, and add all possible edges on those nodes. And the goal is to determine with high probability which of these cases happened, which distribution did your graph come from. And the algorithmic question that goes with it is for which parameters k, for which size of a clique that you plant, is this possible in polynomial time? Okay, so this problem goes way back, like 40 years, and the literature is vast, so there's not a time to do a complete survey of it. But let's talk about some kind of basic things. So what happens if the size of the clique that you plant is constant, like 1,000 nodes or something? Well, then, as the size of the graph gets large and to infinity, this problem becomes information theoretically impossible. You can't distinguish the distributions. So when does the problem get interesting? Well, it gets interesting as soon as the size of the clique that you add is larger than the size of the maximum clique in gn half, which is very tightly concentrated around 2 times log n. Okay, so as soon as you add a 2.1 times log n size clique, you just solve the max clique problem in this graph, and you can distinguish between gn half and this planted distribution. But because I had to make the size of the clique logarithmic, the naive algorithm for solving max clique in this graph, which is enumerate all subsets of size, say 2.1 log n, and check if any one of them is a clique, this requires quasi-polynomial time, because there are n to the order log n such subsets. Okay, so some trivial algorithm works when k is at least 2 log n or a little bigger, but it requires quasi-polynomial time. What happens if we want to run in polynomial time? Well, then the best thing that we know how to do is a spectral algorithm due to Alon, Krivlevich, and Sudakov that uses the second eigenvalue of the adjacency matrix of this graph to distinguish between planted and random. But it will work only when the size of the clique that you plant is at least square root n, so some exponential factor larger than what we were able to handle in quasi-polynomial time. Okay, so these are the most basic 2 algorithms for this problem, one in quasi-poly time and one in poly time. And the huge exponential gap between the two leads to the following hypothesis, which we'll study for the rest of the talk, called spectral is best. Okay, the spectral is best hypothesis says that as soon as the size of the clique that you plant gets below this square root n threshold at which the spectral algorithm works, actually no polynomial time algorithm can distinguish with decent probability between planted and random. Okay, this is the hypothesis. Now, why on earth would you study this thing? So what the heck? Why am I talking about this planted clique problem, the spectral is best hypothesis? So first, there's some really nice payoff if this hypothesis turns out to be true. Okay, if it's true, you get all kinds of computational hardness results for problems that we don't know how to prove are hard in any other way. These are problems like sparse PCA, some in general problems from machine learning. There's a construction of one-way functions. It's a bit beside the point, but you would prove p not equal np. But there's some common theme to problems on this list. One feature of them is that they are often problems which come with a distribution on their inputs. So the inputs are sampled according to some specified distribution, like the role that gn half and the planted distribution play for planted clique. And if you want to prove hardness of such a problem via a reduction, it's nice to start your reduction with a problem which has this feature, like planted clique. Okay, another common feature of these things, these problems that you can prove hardness for, is that they often are problems with quasi-polynomial time algorithms, again like planted clique, and again for the same reason, if you want to prove such a hardness result by reduction, it's nice to start with a problem that itself has a quasi-polynomial time algorithm. Okay, so if spectral is best, if this turns out to be true, we get some pretty nice payoffs. If it's false, for reasons that we'll see soon enough in the talk, it would seem to require some really new algorithmic ideas. You would need some really kind of new algorithm to go beyond this spectral threshold. So either way the cookie crumbles, either way the hypothesis stands or falls, there's some pretty nice payoff. Okay, so hopefully you're convinced that at least it's worth studying this thing. So now let's kind of array some evidence on either side. Like, should it be true? Should it be false? So why would you believe this thing? Why would you believe that spectral is best? Well, one reason is that there's been no algorithmic progress in 20 years. Actually, this is a bit of a lie. You can sort of get the constant in front of the square root n down as far as you want, but you can't get to n to the 0.49 or n to the 0.499. But this seems to be saying that there won't be an algorithmic breakthrough because there hasn't been one. So this is not that good a reason to believe you will never get below the spectral threshold. What about something else? What if we tried to prove this thing, at least conditioned on some complexity theoretic hypothesis? Like, what if we tried to set up a reduction? Let's reduce 3-sat to planted Clique. Okay, here there seems to be some mismatch in the kinds of problems we're considering. NP-hard problems are really about worst-case hardness, and we're interested in proving that something is hard when the inputs are sampled according to a specified distribution, or a pair of specified distributions. So it's not clear how you set up a reduction like this. So in the absence of evidence of this form, like a reduction, what we would like to do is rule out large classes of algorithms. Okay, and this is a project the theory community has been engaged in for 25 years or something now, which is formalize what it means for an algorithm to use such and such a technique, and then show that no algorithm which uses only that technique can go beyond the spectral threshold, can get to n to the 0.49 in polytime. So all the way back in '93, Mark Jerram showed that Markov chain Monte Carlo-based algorithms can't go below this square root n. 10 years after that, Feige and Krautgammer showed a lower bound for algorithms from the so-called Lovász-Schreiber plus convex hierarchy. 10 years after that, these so-called statistical algorithms are ruled out. And if you don't know what these are, it's not a big deal. The point is that these are some pretty broad classes of algorithms that we know don't go below this square root n threshold in polynomial time. Okay, so these are some reasons why you might believe that the spectral algorithm is best. Okay, why might you believe the opposite? Why might you think it could be beaten in polynomial time? Okay, there are many reasons you could believe this, but there's one that I want to focus on for this talk, which is the so-called sum of squares algorithm. Okay, so this is some candidate algorithm that's emerged in recent years. It's super powerful, we think, hence Superman likes it. That has emerged as a candidate challenger to this spectral is best hypothesis. Maybe this guy can go below the square root n threshold. So why might you think that? So what is this thing? We'll see more in a minute, but for now it's some generalization of strong algorithmic techniques like linear programming, semi-definite programming, spectral methods, that seems to be qualitatively different from other such generalizations of these techniques. And here are some pieces of evidence that we've amassed for that. One is that we now know that among all polynomial-sized semi-definite programs for constraint satisfaction, sum of squares, which is itself some very large polynomial-sized semi-definite program, is the optimal one. If you want to do constraint satisfaction with semi-definite programs, you should just use the sum of squares one. We don't know how to write down any hard instance of infamous problems like max cuts or unique games. We don't know how to write down any instance that can't be solved by sum of squares in polynomial time, exactly. But perhaps most relevant for this talk is that over the last few years, we've seen a raft of papers giving improved algorithms for planted problems using sum of squares. So these are problems like planted CSPs, dictionary learning from machine learning. We'll see some tensor problems actually in the next talk, but a wide range of tensor problems. And in many of these cases, there was some corresponding spectral algorithm for this setting, for whatever setting you were considering. And sum of squares came along and beat the naive spectral algorithm for these problems. Okay, it improved the parameters that you could handle in polynomial time. So this is some pretty strong evidence that maybe it should be capable of beating this naive spectral algorithm in the case of planted Clique. Okay, so here's the question: does this spectral is best hypothesis withstand the attack from the sum of squares algorithm, or can sum of squares also not go beyond this the square root n threshold? And the theorem is that the spectralist best hypothesis still stands. So a little more formally, sum of squares algorithms require quasi-polynomial time to distinguish between planted and random distributions when the size of the clique that you plant goes substantially below the square root n threshold, like n to the 0.49. Okay, so this is the theorem. And in the second half of the talk, I want to give you some sense of how you would prove such a thing. But first, are there any questions about, is it clear what the theorem statement means? Okay, great. So what is this sum of squares algorithm first? We have to say a bit more about it before we could say how you would rule it out. So have in mind, as we introduce this thing, fix in your mind your favorite nasty optimization problem. My favorite one for this talk is, given a graph, find the maximum size clique in it. Okay, of course, if you could solve this, you would, in polynomial time, you would hugely beat the spectral algorithm. What is this sum of squares thing? Sum of squares gives you a hierarchy of increasing strength, but also increasing size, semi-definite programming relaxations of your underlying optimization problem. Okay, so here's a picture. So this, our ladder illustrates the hierarchy, and down at the bottom of the hierarchy, we have small semi-definite programs. Like if your input size is n, maybe this semi-definite program optimizes over n by n matrices. Okay? And as you walk up this hierarchy, as you walk up the ladder, you add variables, and you add constraints on these variables, until at the top you get some enormous exact semi-definite program. So by enormous, I mean that it has, say, exponential side length matrices. And exact, I mean there's no integrality gap. It captures exactly the problem you started with. But of course, it's so big that we don't expect to solve it in polynomial time, in general. But on the way up, there are all these semi-definite programs in the middle, all these candidate algorithms in the middle. When this degree parameter d that goes up as you go up the ladder is constant, these things usually correspond to polynomial time algorithms. And these improvements in other settings, in other planted problems, very often come from solving the semi-definite programs that occur at d equals 4 or d equals 10 or something like this. Okay? So for us, we want to rule out those kinds of algorithms for planted clique. That's our goal. And the regime of interest for us will be when this degree parameter d that roughly tells you the size of the semi-definite program that you're working with is less than log n. Once it becomes log n, the algorithms already look like they're running in quasi-polynomial time, and we know that you can already solve planted clique there. Okay. So a little more precisely, what is the algorithm that we have in mind to possibly solve planted clique that we want to rule out? Okay, so here's the algorithm we have in mind in cartoon view. You get a graph. The graph has some family of cliques. We'll think about taking the indicator vectors of those cliques and take their convex hull. That's the clique polytope for the graph. That's in blue and gray in the middle. All right. If you could optimize over that, it has optimum something like 2 log n, which maybe is not so visible, but in red it says 2 log n. If you could optimize over that, you'd be solving max clique. Instead, you solve some relaxation R, which is the big green blob. All right. So you'll optimize the size of a clique, size of a point, going upwards over this green blob. And if your relaxation says that the size is bigger than n to the 0.49, you'll say that you're in the planted case. Otherwise, you'll say you were in the random case. So if it's really standard, you're just thresholding on the value of a relaxation of max clique. Okay? And the relaxation we'll use is like the degree d sum of squares relaxation for d less than log n. So this is the algorithm we want to say does not solve planted clique. All right? Now, let's think about what would make this algorithm succeed. What would make it succeed is if the value of the relaxation, the value of sum of squares, the biggest size point in this SOS relaxation, had value like n to the 0.1, say, when the graph is sampled from gn half, when we're in the random case. So why is that? Because the value is, of course, at least n to the 0.49 in the planted case, and so this value will now distinguish between the planted case and the random case. Right? So there's two possible worlds illustrated here. In one world, the value is like n to the 0.1. In this case, we would have an excellent algorithm. And in this other possible world, the value is actually like n to the 0.49 in the random case. So the sum of squares relaxation says that there's a clique of size n to the 0.49, even when the graph is sampled from gn half. And we would like to show that this picture on the right is what obtains. Right? This is what really happens. And that will show that you can't use this value to distinguish between planted and random graphs. Okay. So our goal, a little bit more formally, is to construct feasible points for this green relaxation, the sum of squares d relaxation. Right? We want to say that given a graph, I can construct a feasible point x of g that's feasible for sum of squares. It lives in this green blob. And in expectation, when my graph is sampled from gn half, the size of my feasible point, so the size of the clique that it supposedly corresponds to, is at least n to the 0.49, even though there's no n to the 0.49 cliques in this graph, of course. And notice that because sum of squares captures spectral methods, actually there's an upper bound of square root n on how big you could ever hope to make this be. So we want to sandwich our thing between this root n and n to the 0.49 kind of bound. And there's actually some prior work on doing constructions like this. Okay? So if instead of sum of squares of degree d, you asked only to prove a lower bound against some less strong relaxation, like linear programming or basic semi-definite programming or some weaker convex hierarchies, actually we know a very natural construction that gives you exactly what you want. It's a point that it's feasible for these weaker hierarchies, at least with very high probability, and it has very high size, n to the 0.49. Okay, and this is how you prove these older lower bounds against weaker hierarchies. And you could take this construction that was used to prove the lower bounds against weaker hierarchies, and you could try to apply it to sum of squares. And actually, people did this last year, last year mostly. And it gives you something. It tells you that the sum of squares value is at least like n to the 0.001 for large constant d. So it tells you some kind of lower bound against sum of squares, but it doesn't give you the tight lower bound that you want. Okay, there's some adaptation of the construction that maybe works at very small degrees, like degree 4 sum of squares, but basically as the degree gets moderately large, this construction doesn't work, and actually in some formal sense. Okay. So what we need, there's this old construction that worked for weaker hierarchies, but we need a new one. So our goal is give a new construction of some point that lives at the top of this green blob in expectation it has very large size and is feasible for sum of squares. So this is our goal. And unfortunately, constructing points that are with high probability feasible for this sum of squares relaxation turns out to be a really non-trivial task, okay? Because checking feasibility for this thing is pretty hard. The technical reason, I guess, is that the space of high-dimensional positive semi-definite matrices is very complicated and sort of not that well understood. So what's the best thing to do when you're faced with some difficult construction? You don't know even where to go looking for a point that would satisfy it, that would do what you want. Well, the best thing is to make your problem harder, make your life harder. So here's the new goal that we try to attempt. And it's some strengthening of the old goal. And we call this pseudo-calibration for reasons I can't get into. And the goal is this. Construct your feasible point x. Right? It takes graphs. It gives you back feasible points. In expectation, the size of this feasible point is supposed to be large. But I actually want this feasible point to share some more properties of a planted clique than just large size. Size is one thing that makes this point look like a clique. Its size is n to the 0.49. That's the size of the clique I'm planting. But I wanted to share some other properties of a planted clique. Okay, and here's a little bit more formally what I mean. Suppose I have some family of test functions, t sub g. All right, and these are functions that take a point in whatever space my relaxation lives in and give me a real number. And what I would like is for some fixed family of test functions, that if I apply my test to my construction, yet to be, I haven't told you how to construct this thing, but I apply my test to my construction, and I look at this in expectation over gn half, that this will give me the same number as if I applied my test to an actual planted clique, looking at this in expectation under the planted distribution. Okay, if you replace t sub g with size, you would get exactly the thing we desired earlier. But now I'm going to ask for it for some broader set of tests. Okay. Why would you do this? Well, one reason would be that you would narrow down your search space for where to look for construction like this, because now I'm placing more requirements on it. So let me say some quick example of what a test like this might look like. And then we'll state a lemma and wrap up. So one kind of test that you might look at maybe would be the test that when given an indicator vector for a clique, tells me something like the number of 4 cliques that contain a typical vertex in the large clique. Okay? So this is a kind of test it turns out that you wouldn't have been able to consider in previous constructions of feasible points for weaker hierarchies. Okay, so why on earth would you consider some family of tests like this? I know this is some very confusing kind of definition. It turns out that if you pick a particular family of test functions, okay, something about low degree functions in the adjacency matrix of your graph, if you pick a particular family of test functions, and you 30 seconds, and you have a construction that satisfies all of these tests, but I don't anymore guarantee you that this construction is actually feasible for the sum of squares. If you satisfy all of these test functions, and you satisfy some not so hard to get small norm condition, then actually this is sufficient to be feasible for sum of squares with high probability. So we had some old goal that was construct a feasible point for sum of squares. We replaced it with a harder goal, which was be feasible and satisfy lots of tests. But it turned out that satisfying lots of tests was actually enough for feasibility. Okay, so the second lemma of the paper is that actually a construction satisfying these above conditions exists. Actually, it turns out that once you know the conditions, there's only really one construction to choose, so you have to choose it. And it follows that sum of squares thinks there's an end of the point 49 size clique in Gn half. Okay, so wrapping up, we basically solved this SOS versus planted clique problem using some new approach called pseudo-calibration. And actually, pseudo-calibration is pretty general. It doesn't apply just to planted clique. We think it should give constructions for sum of squares lower bounds and maybe algorithms for other kinds of planted problems. So go forth and pseudo-calibrate. Thanks very much.
We have time for probably 1 or 2 questions. Nobody has any questions. Okay, let's thank the speaker again.